Hi everyone, I'm Anjiang Wei, and today I'm going to present my work on free lunch for testing, fuzzing deep learning libraries from open source. This is a joint work done by me and my collaborators, Yinling, Chenyuan, and Lingmin. We are from Stanford, Illinois, and Nanjing University. Let's begin with the background knowledge about deep learning libraries. From a user's perspective, we usually use these libraries to build a DL model, which consists of 3 steps. Firstly, we need to define a model by writing a DL program. Secondly, we need to prepare and load the dataset. Finally, we can train the model and run the inference. In order to help users build a model efficiently, DL libraries usually expose their APIs in Python. Also, DL libraries usually integrate different backends for flexibility and performance, thus providing a unified abstraction for different hardware, including CPUs, GPUs, mobile devices, etc. In this work, we focus on detecting bugs in DL libraries. Prior work called Cradle is proposed to use differential testing as the test oracle. Basically, Cradle takes existing models, runs the models on Keras, which supports different backends, and compares the results between different low-level libraries to find inconsistencies. A more recent work called Lemon proposes the idea of applying model-level mutation rules to generate more DL models to test the libraries. Here, we show some of the model-level mutation rules designed by Lemon. Layer addition simply adds a new layer to the original model, and the constraint here is that the input and output tensor shape need to be exactly the same. The third rule, called layer removal, can remove a layer whose input and output tensor shapes are identical. The last 2 rules, activation function replacing or removal, can work because activation function does not change the shape relations between input and output tensors. We then discuss the limitation of prior work. Prior work uses model level testing, which only covers a limited number of APIs. In reality, DL frameworks usually have thousands of APIs, while we find that models used in prior work can only cover at most 59 APIs. Besides, the model level mutation rules proposed by Lemon are too constrained. As we discussed before, the intact layer mutation requires that the output tensor shape of the API to be added or deleted should be identical to its input tensor shape, thus causing these mutation rules hardly generalizable to a huge number of other APIs in the DL libraries. In this work, we present FreeFuzz, a fully automated API-level fuzz testing framework. One challenge here is how can FreeFuzz automatically invoke a given API? The challenge exists because the APIs in DL frameworks are mainly exposed in Python, a dynamically typed language. Therefore, it is hard to determine the parameter types for test input generation. Moreover, there may also be complex constraints among parameters. Let's take a look at conv2d API's definition in PyTorch official documentation. Based on the API definition itself, we can hardly infer type information for its parameters. Luckily, for this widely used API conv2d, the documentation says that in-channel is an integer, and stride can be either integer or tuple. Also, the parameter called groups is an integer, but it has a constraint that 2 parameters called in-channel and out-channel must both be divisible by groups. If the constraint is not met, then some exceptions will be raised. Next, we'll discuss how we resolve these challenges. There are actually code snippets there in the documentation showing users how to invoke this conv2d API. Our idea is that if we can run those code snippets and dynamically trace the API invocation, we will know enough information on how to automatically invoke APIs. Next, I will gradually show the overview of our approach, FreeFuzz, which is mainly composed of 4 stages. The first stage is code collection. As shown in the figure, FreeFuzz obtains code from 3 different sources: code snippets from library documentation, library developer tests, and various DL models in the wild. all of which can be obtained from open source automatically. The second stage is dynamic tracing with instrumentation. FreeFuzz first hooks the invocation of APIs, then executes the code collected in the first stage to trace the dynamic execution information for each API invocation. As a result of the second stage, FreeFuzz constructs the type space, API value space, and argument value space for later fuzzing stage. The third stage is called mutation-based fuzzing. Basically, FreeFuzz effectively generates mutants for the test input used to invoke the targeted APIs based on the traced information collected in the second stage. The mutation strategies are composed of type mutation, random value mutation, and database value mutation. The last stage is running all the generated tests with oracles. FreeFuzz resolves the test oracle problem by differential testing and metamorphic testing on different backends and hardware. FreeFuzz is able to detect various types of bugs, including run computation bugs, crash bugs, and performance bugs. We'll next go into the instrumentation stage in detail first. In the instrumentation stage, we design a simple type monitoring system called FuzzType. The goal is to record more information to better guide fuzzing. It is a finer-grained type system than Python's native type system. For heterogeneous data types like tuple and list, Python's type system only informs us that this is a tuple or list, while FuzzType will record the type of each element in the tuple or list. In this example, a total of 2 integers. For tensor objects, in this example, Python only informs us that this is a torch or tensor object, while FuzzType will record that this is a 4-dimensional tensor with float32 as its data type. With such finer-grained information, FreeFuzz can better conduct fuzzing in the later stage. In the instrumentation stage, FreeFuzz will also construct the API value space. Each entry in the API value space represents one API invocation. More specifically, in that one entry, we record each argument's value and type, and the input tensor's shape and data type. The reason for constructing API value space is to serve as seeds for mutation-based fuzzing. During the fuzzing stage, FreeFuzz will randomly select one entry from the API value space and then mutates the argument values and types. But we will cover the fuzzing stage in detail later. After constructing the whole API value space, FreeFuzz will then construct argument value space. The argument value space is constructed by aggregating the information from API value space to speed up the queries to our database. More specifically, the role of each entry is argument name and its type. For example, for both conf2d and conf3d, they share the argument called in channels, which is an integer. The column of each entry is the API name and its recorded values. In this example, we can see that conf2d and conf3d have different values recorded for the same argument. The argument value space is constructed for fuzzing similar APIs. For example, to generate values for in channels for conf2d, FreeFuzz can sample values of in channels from conf3d, because we believe that values for an argument of one API can serve as potentially reasonable values for the arguments of similar APIs. We formalize this idea as database value mutation, which will be discussed later. Next, we will focus on mutation stage. We now show the overview of our mutation algorithm. The input to our algorithm is the API under test, API value space, and argument value space. And the output of our algorithm is the mutated arguments. So after mutation, FreeFuzz can invoke the API under test with mutated arguments for fuzzing. Here, we show a simplified description of our algorithm. At first, randomly samples one entry in the API value space. Then for each argument in that entry, it randomly decides whether to apply mutation to that argument or not. If FreeFuzz decides to mutate that argument, it then computes its fuzz type. Afterwards, it randomly decides whether to apply type mutation or not. Finally, it will randomly make a choice between random value mutation and database value mutation, then mutate it based on the type information. As we can see, our approach consists of the three following rules: type mutation, random value mutation, and database value mutation, and I will elaborate on them later. For type mutation, our strategies are based on fuzz type. In the table below, T1 is its original type and T2 is its type after mutation. FreeFuzz can mutate tensor's dimension or shape, mutate tensor's data type, for example, changing from float 32 to float 16, mutate Python's primitive type into another, and mutate types of elements in collections of heterogeneous objects. After introducing type mutation, we next talk about value mutation, which include random value mutation and database value mutation. For random value mutation, it is quite simple because it just needs to generate random values based on the fuzz type. In this example, InChannel has an integer type, so we can generate a random integer for it, then invoke the API. For database value mutation, it's very interesting. The goal of database value mutation is to use trace values from similar APIs to test the current API. It leverages the argument value space that we introduced earlier. In terms of how we determine whether two APIs are similar, we use this formula. It is based on the API definitions, which are text, or in other words, strings. We get the Levinstein distance between the current API and all other APIs sharing the same argument, normalized by their maximum length. So if the two APIs definitions are similar, then the distance should be low. So our similarity score should be high. We then transform the similarity score into probability for sampling APIs by applying the softmax function, so that the more similar APIs will have higher chance to be sampled. After randomly sampling one API according to the probability, FreeFuzz will then randomly sample one recorded value of that argument from that sampled API. The last stage of FreeFuzz is the oracle part. We can detect three different types of bugs. One category is called wrong computation bugs, and they can be detected via differential testing between CPU, GPU without with cuDNN disabled or enabled. Another category is performance bugs. We detect them by metamorphic testing. Our insight is that on GPU, tensors with less precision data type should execute faster. For example, API invocation with float 16 tensors should execute faster than float 32 tensors on GPU. Also, FreeFuzz can detect crash bugs. For wrong computation bugs, here we show an example bug that FreeFuzz detected for the widely used comp to the API. By comparing the GPU results with cuDNN enabled against computation results with cuDNN disabled, we find that the results computed without cuDNN support is incorrect. This bug has been confirmed and fixed by PyTorch developers. Next, we'll talk about the experiment. The first research question is, how do three different input sources of FreeFuzz without any mutation contribute to DL library testing? Our metric here is the number of covered APIs and the line coverage. And we break down the input sources into three different parts. That is the documentation code, library developer tests, and DL models. Our conclusion is that all three sources of input count, having its unique contribution to the number of covered APIs or the line coverage. Next, we will talk about the coverage trend analysis and our ablation study. We generate 1,000 mutants for each API, and the runtime is within 10 hours for both PyTorch and TensorFlow, which is totally acceptable for fuzzing. The x-axis of our figure is the number of generated mutations per API, and the y-axis is the overall line coverage. As we can see from the figure, 600 mutants is probably a cost-effective choice in practice, because after generating 600 mutants per API, the line coverage is largely stable. Besides the full mode of FreeFuzz, we also show 3 variants of FreeFuzz. Each variant is turning off one of its 3 mutation strategies. As we can see in the figure, turning any one of the mutation strategies off will result in fewer covered lines. So our conclusion is that all 3 mutation strategies are effective. Also, as we can see in the figure, turning off the type mutation has the lowest line coverage, demonstrating that type mutation is the most effective one. The potential reason may be because the lower level implementation for different tensor data types tend to be different. For example, integer tensors and float tensors will invoke different code. We also compare FreeFuzz against prior work in terms of covered APIs and line coverage. In terms of input source, FreeFuzz considers all 3 input sources, so it is better than Lemon and Cradle. FreeFuzz achieves much more APIs coverage and also has the highest line coverage. We also compare our API level mutation with Lemon's model level mutation. We show that FreeFuzz can cover around 9 times more API with around 3.5 times less overhead. Also, FreeFuzz can achieve 1.2 times more line coverage than Lemon. So far, FreeFuzz has detected 49 bugs in total, and 38 of which have been confirmed by developers as previously unknown bugs, and 21 of them have already been fixed. Also, we demonstrate here that each mutation strategy can help detect certain bugs, demonstrating the importance of all 3 mutation strategies. Next, we will show more bug examples. This is bug detected by FreeFuzz in Conf3D API. It crashes if we set the padding mode to be reflect. FreeFuzz finds these bugs thanks to the database value mutation, namely using values from similar APIs for fuzzing. More specifically, Conf2D supports padding mode to be reflect, but Conf3D crashes unexpectedly for reflect. The bug is triggered when FreeFuzz samples the values from supported values of padding mode from Conf2D to generate value of padding mode for Conf3D. According to the documentation, reflect should be supported in Conf3D, while actually it is not supported. The bug has already been confirmed by developers. Here we show another bug found in Max Unpool 2D. This bug is an interesting one because for the same input tensor, it throws an exception on CPU but passes silently on GPU. After inspection, we find that the exception is expected because the input is actually invalid. So GPU produces a wrong result silently without throwing any error. FreeFuzz finds these bugs because it applies random value mutation and differential testing. Moreover, from this bug, we can see that FreeFuzz does not always generate valid test input, which can also help to detect certain interesting bugs. This bug has been confirmed by developers and even labeled with high priority. In conclusion, in this work, we propose FreeFuzz, the first general purpose and fully automated API level fuzzing for deep learning libraries. The reason why we call it a free lunch for testing is because FreeFuzz mines code snippets from library documentation, developer tests, and DL models in the wild, which can all be obtained from open source. After that, FreeFuzz mutates the traced value, traced input via type mutation and value mutation. It can detect various bugs via differential testing and metamorphic testing. It's worth noting that our idea of fuzzing from mining is generalizable to other dynamic settings. So far, FreeFuzz has detected 49 bugs for PyTorch and TensorFlow, with 38 of them confirmed by developers as previously unknown. FreeFuzz can also cover 9 times more API than prior work, with only 3.5 times lower overhead. Our code is publicly available. Thanks for your attention.